Sure.
Thank you.
Sure.
Okay. Hello, everyone. My name is Pham. I'm from the University of Minnesota, Twin Cities. And today I will present about the Cantor-Rick duality theorem, which is the main theorem in the optimal mass transportation studies and the Wasserstein quotient space. So this one is my RU research project with my advisor, Professor Wilfried Gangbo at the UCLA this summer. Here's the outline of my talk, which is divided into 4 parts. So first, I will this is an introduction. So for a brief history, optimal mass transportation dates back to Gaspard Monge in 1781 in France, and 160 years later, a significant advancement made by Leonid Cantor-Rick earned him an economics Nobel Prize. Optimal transport has a lot of connections with other areas such as PDE, fluid mechanics, geometry, probability theory, and functional analysis. Currently, optimal transport is used in image processing, cancer detection, and machine learning, to name but a few. So here's the medical application of optimal transport. So because human cells tend to move in an optimal way that use as low energy as possible, then optimal mass transportation can be used to simulate the movement of cells in the body. So what is actually the optimal mass transportation problem? First of all, I will introduce to you a notation that I will use throughout my talk. So this is the Dirac mass, as known as the point mass. Given a point P in a set X, we define the function delta P of E to be 1 if P is in E and 0 otherwise for all subsets of the set X. I will use a factory warehouse setting for explaining the optimal transport. So on the left, we have a set of factories, which is X1 and X2, with a goods distribution among them of 3/4 and 1/4. And on the right, we have a warehouse set with Y1, Y2, with a distribution of the capacity, the storage capacity to be 3/4 and 1/4. So the job for the logistic company is to transport the goods from the factories to the warehouse. So here's the Monge problem. The Monge problem is to transport the goods in the optimal way for the cost without splitting the goods on the way. So here's a transport plan for the Monge problem, and it turns out to be the unique one when we transport 3/4 of the goods from X1 to Y1 and 1/4 from X2 to Y2. Then for each journey, we have a cost per unit mass. So in this case, the cost to transport a unit mass from X1 to Y1 or X2 to Y2 is 1. And the cost per unit mass to transport from X1 to Y2 and X2 to Y1 is 10. And according to this cost per unit mass, this Monge plan that I have just shown you costs 1. So the Cantor-Rick problem sets up the same set of factories, warehouse, but then we can split the goods on the way. So that here's the transport lane for the Cantor-Rick problem, where we transport 9/16 of the goods from X1 to Y1, 3/16 from X1 to Y2, 3/16 from X2 to Y1, and 1/16 from X2 to Y2. And with the same cost per unit mass to transport as in the previous slide, we have the cost for this transport plan to be 13/4. Next is the formal statements of the Monge problem. So the Monge problem is to find a transport map T from the starting set to the destination set, satisfying the push-forward conditions such that it minimizes the cost functional as written on the screen. So because the starting set and the destination set can be continuous, not discrete, as in the example I shown you, we write the integral instead of the sum for all the costs. So C is the cost function. And the notation for push forward is that the push forward condition means that the size of the destination set is equal to the size of the starting set. For the Cantor-Rick problem, first we define the projections. So given a measure gamma on a cross product measure space X cross Y, we define the projections by this formula. Then we use that projection to define the set of transporting planes. So the set of transporting planes is big gamma of mu0, which is the starting distribution, and mu1, which is the destination distribution. It's a set of Borel probability measures on the cross product of the space, which has the first marginal to be the starting distribution, and the second marginal to be the destination distribution. So that the Cantor-Rick problem is to find the cheapest transport plan to minimize the cost function, which is the total of the cost across all the transporting plans. So in fact, we can write the minimizing problem into a maximizing problem via the duality theory. So the duality formulation is here, so that the duality problem is to find a pair of bounded continuous function such that ux plus vy is less or equal than the cost function for all x in x and y in y, to maximize the duality function here. So next, I will talk about some background materials before I move on to the main part of my research. So first of all is the narrow convergence. So we say that a sequence of measure converges narrowly to a measure mu if the integral of f with respect to mu n converges to the integral of f with respect to mu for all bounded continuous function on a set X. A reminder of the convergence in metric space is that if a sequence xn in the metric space M equipped with the metric D converges to X, if xn gets closer and closer to X with respect to the metric. Next up, quotient space, but first we need the definition of the equivalence relation. So a binary relation on a set X is an equivalence relation if it satisfies the reflexivity, symmetry, and transitivity. And the equivalence relation will partition the set X, and we call the set Y of equivalent classes of X the quotient set. For some linear algebra, I will talk about orthogonal transformation, where linear transformations that satisfying O times O transpose is equal to O transpose times O and equal to the identity matrix. An important property of the orthogonal transformation is that they reserve distance. So here's the main first part of my research, which is to imply the Cantor-Rick duality theory from discrete to continuous. So we start with a result from Pham research paper in 2018. So consider two sets, X and Y, each of n points, and the cost function C from X cross Y to the non-negative real number. And then we set the measures on X and Y to be the average Dirac mass of the points in the set. Then the set of transporting planes from X to Y is gamma of mu0n, mu1n, which is like the discrete transporting planes. And also we let U to be the set of pair of bounded continuous functions with satisfying ux plus vy is less or equal than the cost function. The result from previous paper says that the Kantorovich quantity is equal to the duality formulation, so that we have the duality theory. So if we set the cost function to be the square of the distance, then the Kantorovich quantity Kn becomes the square of the quadratic Wasserstein distance between mu0n and mu1n. So that's throughout this presentation, I will use W2 square instead of Kn. To imply the continuous, like the general case, we will write the integral instead of the sum. So that we want to show that with arbitrary probability measure mu0 and mu1, W2 square of mu0 mu1 is equal to the general duality formulation of mu0 mu1. So this is an intuition of my proof, so that we want to approximate the general quantities W2 and D infinity by sequences of discrete quantities. So that here is the discrete quantities and here's the general quantities. So that because of the previous paper, we know that the two quantities on the left are equal to each other, then we can imply the equality on the right. And because the cost function and the functions in the duality formulations are continuous, we can think of finding some discrete sequence of measures mu0n and mu1n converge to mu0 and mu1 in the sense of narrow conversions. But we don't use narrow conversions directly, but we use a metric to approximate. So we consider the space PV of RD of probability measures in RD with P finite peak moment. And we define the metric WP of mu and V to be this formula, which looks like the narrow conversions. And we approximate the three measures in P1, mu0, mu-n, and the transporting blend by the metric W1. So we have the first proposition that let mu be a Borel probability measure in P1 of RD. Then there exists a sequence mu-n of average of Dirac masses that converges to mu in the metric space P1 W1. To do that, we approximate the probability measure mu by a probability measure mu supported by the cube large enough such that the measure of each rectangle in the cube is positive by some approximation that I am not showing here. But then with that, we can do the splitting of the cubes into smaller and smaller cubes. And then we take the center of each of the cube, then set up the sequence of our discrete measures by mu-n with this formula, which is the sum of Ti times the Dirac mass of each of the center of the cubes. Ti is not necessarily in the form of 1/n, but then it can be approximated by a rational number Si/n, and then we can repeat the Dirac mass of the center many times as needed to have the average of Dirac masses. Next one with the two sequences of measures, as we have just found, that converges narrowly to mu0 and mu1. Then we have some comparison. That is the limit of the discrete duality formulation is less or equal than the general duality formulation of mu0 and mu1, and the W2 square of the discrete measures, the limit of them is greater or equal than the W2 square in general. Then we include the two inequalities together because due to the resist paper, these two quantities are actually equal to each other. And then we have the first comparison that the W2 square mu0 mu1 is less or equal than the general duality formulation. Indeed, it is easy to see the opposite direction because of the constraint condition of Ux and Vy in the duality formulation. Therefore, we have the equality. So we've done with the proof of the Cantor-Ring duality from discrete to continuous. And next one, I will introduce for you the quotient of Wasserstein space by the group of rigid transformation. So the rigid transformation is the linear transformation, which is of the form Tx is Ox plus C, which includes the rotation by 90 degrees and the shifting. So a remark is that rigid transformations reserve distance. Then we define an equivalence relation on the space P2 by push forward by rigid transformation. So this is natural because if you have an object, then you want to rotate it and shift it, then you have the same object. The rigid transformation will not change the shape and the size of the object. Then we define the quotient metric W2R of mu0 and mu1 by the minimum of the Wasserstein distance of mu0 and an element of the equivalence class of mu1. And W2R is the metric on the quotient space under the equivalence relation by rigid transformation we have just defined. So this metric, this quotient metric is useful in the when we calculate the distance between the two classes of measures, not the measures individually. So this is the end of my talk. Thank you for listening.
Thank you.